Okay, welcome to the third Hangout for Higher Revision. I hope you're joining the Hangout tonight. The plan for this evening is to go over maybe about 5 or 6 questions from the Higher which have been selected to sort of give you that little bit extra practice. Now you can watch, you can write down the answers, and you can review the whole little show again when you get the YouTube link. So I'm ready to start, so I hope you're all sitting comfortable with your pens and paper and your calculators ready, and I'll present the answer to the questions to you, and then you can try them out yourself and watch how they're done as it happens. So I'm going to stop now then and go to screen share, and once we go to screen share you'll see the first question which you'll be asked to sort of think about tonight, and here it is here. Now there is the first question we look at tonight, and the first thing you'll notice is that it's a projectile problem. Now right away, do not panic. Projectiles cause panic in students, but you shouldn't really bother. So we'll move him out of the way and we'll decide how to start this problem. Let's take a look at it. A ball is kicked at an angle of 30 degrees to the ground with a velocity of 20 meters per second. How high will it be after 0.5 seconds? And the second part says, how far will it be horizontally from where it is kicked? And part C is this type of question you get asked to make you think about your physics rather than go through all the different sort of calculations. Now before you start a projectile problem, you should know your projectile template, and that is this here. That's the thing you should know, and the first thing to do in that is to start to fill in all the data which is in the particular question, and that's really what we start to do then. Now there's the velocity vector here, which we know is 20 meters per second, so that goes in like that, and we know that we have to work out the horizontal vector component, so we make sure we've got a line in like that. And we have to work out the vertical component as well, because in projectiles we can split the motion up into horizontal and into vertical. Now we know the angle is going to be simply 30 degrees. Now we've got a simple little triangle to work out then. We know the component up the way must be 20 times sine of 30 degrees. Now if you do that on your calculator, you get the size of that equal to about 10 meters per second, because as all you mathematicians know, sine 30 is a half. So we have the vertical component of this velocity here to be 10 meters per second. Now what about the horizontal component of it? Well, it's the same idea. The horizontal component we know is going to be 20 times cos of 30 degrees. Do that on your calculator. You should end up with 17 meters per second. Now that's the first thing you do in your template. You work out the vertical component and you work out the horizontal component. And now you start to assemble all the data you have and what you have to try and find. Okay, let's go then. How high will it be after 0.75 seconds? So in terms of vertical motion, the initial vertical velocity will be 10 meters per second, so that goes into your template like that, 10 meters per second. We don't know anything about the final vertical velocity because we're asked to find how high it will be at 0.75 seconds, and we don't know whether that's going to be at the top of the flight or midway through the flight. We just don't know, so we've got to leave out the velocity at that point. We don't know anything about it. We do know the acceleration, minus 9.8 meters per second. We know that. Minus because acceleration is constantly acting downwards. And we want to find the displacement, which is that one here. And finally we've got the time as well. We've got the time to be 0.75 seconds. So we've got quite a bit of data on that left-hand side. On the right-hand side we know nothing about the distance, although we're asked to find the horizontal distance later on. But we do know the horizontal velocity, which is going to be, in this case, 17 meters per second. And we do know the time, in fact, it's going to be in flight for. It's going to be in flight for at that particular point 0.75 seconds. So anyway, we can calculate that first part. But let's go back to the first question. How high will it be after 0.75 seconds? We have got U, we have got A, we have got S, and we have got T. You look up the data book and you should be able to know the famous equation which we have is S equals UT plus a half AT squared. And all you have to do to get your higher marks is plug those numbers into the upwards displacement. The initial vertical velocity is 10. The time it's in flight for is 0.75 seconds, so we can fill that in. Plus, the only thing that can cause slippages here, half, 0.5, and the acceleration is multiplied by minus 9.8. So make that clear in your calculation. And then finally times 0.75 squared. So there we've got all our calculation there. Take your time in the calculator. If you do that in the calculator, you should end up with the height of the displacement upwards to be 4.7 meters. You can check that calculation later on. So that's what we have in this particular situation. The ball is going to go up into the air and is going to come down, but we know at 0.75 seconds it will be some height in the air, and that height will be 4.7 meters, sorry. So that's how you do the first part. Part B, how far will it be horizontally from where it's kicked? How far horizontally from where it's kicked at that height? And the whole answer is waiting for you, because your template will work. Horizontal distance is equal to horizontal velocity, 17, multiplied by the time, 0.75, and you work out your calculated horizontal distance at that point will be 12.8 meters. So that's a good question for you, and the reason why we won that question was because we were organised. And you must be organised, because you must put down this template, the vector, work out the horizontal and vertical components. That's easy enough. And then be confident to work out the vertical motion, U, V, A, S, and T. And at the right hand side, have your horizontal distance, horizontal velocity, times time. Fill things in and you get your answer. Now part C of this question is the little foxy part of physics which asks you to think what might happen without any calculations here. And it says if a heavier ball is kicked with the same velocity and angle, will it be higher or lower at 0.75 seconds? Well, look at the question. Did mass come into that calculation? No, it didn't. Mass did not come into the calculation. Mass was not in the calculation. So if mass was not in the calculation, then it means that mass doesn't count. Mass was not in the calculation, so mass does not count. So as long as you fire or kick the ball with the same angle at the same speed, it will always go at that height at 0.75 seconds. It will go at the same height of 4.75 meters, or 0.7 meters, sorry. So mass is not in the calculation, so mass does not count. And that's that little thinking bit, which can give you that extra 2 marks, which would get you the A and the higher. So a projectile problem. Key points. Template. Take your time. Mark everything into your data. Find out what you've got to solve. And that's that. So a good problem for you to watch and listen to when you watch the little movie on YouTube later on. On to our second starter question for tonight. And what will it be? Well, let's take a look. It's one of these questions. Did you know violet light has more energy than red light? Now, how do we know that's true? Is that true or is it false? Well, you have the physics to try and solve this, and the first thing you've got to remember is that light is made up of photons, and the energy of the photon depends on its frequency. In fact, this is the well-known equation here. Energy of the photon is equal to Planck's constant times the frequency of the photon. Now that means that light of higher frequency will have more energy. Now that equation has got a sister equation, and the sister equation for that one is E, same energy, equals same Planck's constant, but this time C divided by lambda. And that's a source of great problem for people because they don't know how to get from there to there, and yet it's a simple standard grade technique. We know that the velocity of any wave is equal to the frequency times the wavelength. Now, because we're dealing with the speed of light is a constant in air. It's a very famous constant, so it's given a letter all by itself. It's given the symbol c. So the speed of light is c is equal to the frequency times the wavelength. Now, it's not a great math step to realise that if you want to get rid of that frequency, you have to change this to frequency, so c divided by wavelength is equal to the frequency, and there you have, if you substitute the frequency by this, you're going to end up with energy equals hc upon lambda. So there is our two main equations. The main one, E equals hf, and the sister one, E equals hc upon lambda. So what does this tell us? It tells us waves of light with very short wavelength, short number here, have got a big energy. So our question is, did you know violet light has more energy than red light? Well, to do that, we must take a look at the spectrum. So if I switch on to this one here, you can see a mock-up of the spectrum. At this particular point, you can see you can move through the spectrum and the wavelength changes. You can see when we go up to the red end of the spectrum, we have a wavelength of 700 nanometers. Remember, 700 nanometers means 700 times 10 to minus 9 meters. So red light has got a long wavelength. Blue light, on the other hand, or violet light, has got a very short wavelength, 400 nanometers. So as young higher students, young physicists, you must know the range of wavelengths which we can see. Violet, 400 nanometers, all the way up to red, 700 nanometers. Now I wonder if that will help us in our previous question to see who was right, or see if this is true or false. Which has more energy, violet light or red light? Well, we now know that violet light has a very short wavelength, a very short lambda. So according to our sister equation, E equals hc divided by lambda, you can see that for a very short wavelength, the energy for violet must be quite high. So violet light has high energy. Violet has high energy photons. Has high energy photons. Sorry, I've got it out for you. Has high energy photons. High energy photons. And correspondingly, red light, which has got a long wavelength, will have low energy photons. So in this particular case, it's true. Violet light has more energy than red light, all because it has a much shorter wavelength. And that's a little sort of diagram you have to remember for that. You have to remember along the lines that red 700 nanometers, violet light 400 nanometers, and that will help you with those particular problems. Now, on the same theme, you might be asked to find a graph which shows how the energy of the photon depends on the frequency. Now, to do that, you go back to the original equation. E equals hf. Now, h is Planck's constant, which means that you're going to have energy directly proportional to the frequency. And the corresponding graph for that should be a straight line like that. So that's the graph you're looking for the energy of the photon plotted with its frequency. Now they could ask you the sister graph. What about the energy plotted with the wavelength? Now in this particular case, you look at the sister equation. Energy equals hc divided by the wavelength. Hc divided by the wavelength. In terms of your proportional, you have E is directly proportional to 1 upon the wavelength, because remember hc is a constant. So in this particular case you have energy directly proportional to 1 upon the wavelength. That's the inverse law. So the inverse law means you start high, low wavelengths will have a high energy, and it will swoop down like that to give you the long wavelengths having the low energy. Now these are two graphs which tell a story which you just got to learn. So take a wee minute when you watch the movie again, rehearse writing out those graphs and rehearse the theory behind it. E equals hf, and the sister equation E equals hc upon lambda. Okay, we're doing quite well. We've now covered a wee bit of the waves and the photons. Let's move on to our next starter question for tonight. I wonder what it will be. Oh, it's density. Now there's a very good picture, because all these rods here are made up of different material, but they've all got the same mass. So each of these rods here have got the same mass, but obviously they're occupying different volumes. And that's what we mean by density. Density of an object is how much mass is in a given volume. Remember the famous suitcase one, where you have a suitcase on your holiday. If you want to go your holiday, you usually start off with the suitcase being quite less dense. And by the time you come back your holiday, you've packed more stuff into the same volume. The case is much more dense. So from the data book, we know that density is given the following relationship. Density is equal to the mass divided by the volume. And that's one of the key equations which people tend to forget when they do the higher physics. They tend to forget this simple wee equation. So let's take a look at the higher question, which is asking our knowledge about density. The density of the gas in a container is initially 5 kilograms per meter cubed. That's another thing you've got to remember very importantly, that the units of density are mass, kilograms, per meter cubed. It could ask you that. So that's the units for density. Which of the following increases the density of the gas? Now, one of these questions, the strategy is go through each of the statements one by one and judge with your physics knowledge whether it's right or it's wrong. Okay, let's go. Raising the temperature of the gas without changing the mass or volume. Well, I haven't changed the mass and I haven't changed the volume. There's definitely no mention of temperature there, so that one's wrong. It's not going to increase the density. In fact, the density is going to stay the same. So number one is false. Move on to the next one. Increasing the mass of the gas without changing its volume or temperature. I haven't changed the volume, I haven't changed the temperature. Temperature's not in it, but I've increased the mass. If I increase this number up here, I'll certainly increase the density. Think of the suitcase, more mass put into the same volume, you will increase the density. Now don't get flushed with excitement, because you've got one statement left and the next statement could be true as well. Let's have a read at it. Increasing the volume of the gas without changing its mass or temperature. Well, I ain't going to change the mass, but I'm going to change the volume. I'm going to increase the volume. And if you increase the volume, you're going to reduce the density. Think of the suitcase. You can't get any more stuff in it. You go and buy a bigger case to make the case less dense. So, in this particular case then, increasing the volume will decrease the density, so that is wrong. So the correct answer is going to be 2 only, and it's the first one, and that's that one done there. So please remember your density, mass divided by volume, and remember also that little equation you'll find in the data book, and these are the type of questions that could be asked from it. Okay, that's density covered. Let's take a look at our next starter question of this evening's revision. Well, here comes the most famous one of the lot, and it's to do with spectra. You have to work out what that colour is there and what that colour is there. Now let's take a minute to look at this. First of all, we've got the white light passing through a prism. Now we know when white light passes through a prism, the light will be refracted, and different frequencies are refracted more than others. Now you have to remember this diagram here for a prism. The prism produces just one spectrum, or one spectrum is the correct word, one spectrum, and it ranges from violet all the way up to red. Violet, indigo, blue, green, yellow, orange and red. Violet, indigo, blue, green, yellow, orange and red. You'll notice that violet is pushed down the most, it's refracted the most. Now that's one diagram you have to remember. So at position X, you're going to have violet light there. Now what the higher examiners will ask, they'll ask you, does this young physicist know the difference between a prism and a diffraction grating? Now a diffraction grating, you won't get one spectrum or spectra, I forget what the plural is, but what you will get is you'll get 2 or 3 or 4 depending on the grating itself or the position of the screen. So if I show you the diagram for that, which you should know, you get this particular setup. And the thing to watch out for here is you'll get more than one spectrum. There's one, and there's the second one. At the center point here, you'll get a white maximum because all the wavelengths meet here, and all the wavelengths, all the frequencies will have the different colors of the spectrum. All the spectrum mixed up together will give you white. And then this side, you'll have the first order spectrum and then the second order spectrum. But what you should notice is this red light, which is furthest away. It's actually red light which is furthest away here. Red light is furthest away. Now we can show this in a wee movie here. There is your laser, there's your diffraction grating, and if I put on a white light source through that, bingo, there's what I get. I get a white central maximum. Don't forget that because I can ask that in the higher. What's your central maximum with the diffraction grating? White light. But there's the first order one. There's the second order spectrum. And there's the third order one. And likewise, on the other side, first order, second order, third order. But what do you notice? I notice that the red light, which is pushed out further. The red light is pushed out further. Now there's a reason for that, and the reason comes from your little equation, n lambda is equal to d sine theta. That is a diffraction equation. If I change for sine theta is going to equal to n, which is the order, first order, second order, third order. Lambda is the wavelength, and d is the spacing between the actual lines of the grating. Now I can see that for very long wavelengths, red light, as we discussed earlier in the tutorial, the angle must be long as well. So the angle is pushed out. This is a great example of how maths is actually helping us explain a physical phenomena. If we get short wavelength, we now know that's violet. Short wavelength, keeping d and keeping n the same, sine theta will be smaller, and it will be. The angle will be smaller. So make sure you understand that grating pattern. Make sure you remember it. Make sure you know where the colours are, especially central maximum, and make sure also that you know the difference between blue light and red light passing through the grating. The red light is pushed out further because sine theta is directly proportional to the wavelength of light. Short wavelength, shortly spaced out, not spaced out as much. Red light, long wavelength, long spaced out. So there we have it. That's a little bit of revision on diffraction gratings and the colours of the spectrum, which you have to learn for the higher, and it could come up in your higher. Okay, let's push on to our next question. And our next question is this one here. And while you're looking at this one here, I'll just check to see if anybody's asked any questions. Oops, sorry, the screens are making. We can come back to that. Sorry, hang on that one. Yeah, so I'll lose the screen, so I have to go back on the screen again. Let's take a look at this question here. It says a pulse of light has an energy of 10 joules. Calculate how many photons make the following transition to give 10 joules. Now this is happening in one of the atoms. An electron, we know, falls down from a high energy level to a low energy level and gives out a photon of light. Now the energy levels are numbered here, and one of the big trip-up points is the minus signs. What does those mean? The minus signs just simply mean how much energy an electron needs to escape the atom from this particular point. So if you're an electron sitting here, you need 21.8 times 10 to minus 19 joules to escape the atom, to be ionized, to get away from the atom. If you're an electron sitting up here, you just need 5.40 times 10 to minus 19 joules to escape. So our problem is work out the energy difference, because when the electron makes that transition, it will give out a photon of energy, which we know is always equal to E, which is also equal to the Planck's constant times the frequency. So if I work out the energy gap here, I can work out the energy of that photon. Now what is the energy of that photon? Well, in the time-honoured fashion, we take the big number. The energy will be equal to the big number, 21.8 times 10 to the minus 19, and take away 5.40, the smaller number, times 10 to minus 19. And we work that out in our calculator. We should get the following. We should get something like the energy level, or the energy gap, sorry, is equal to 16.4 times 10 to the minus 19 joules. So that is the energy giving out by one of these transitions. One photon gives out that much energy when it makes that transition from there to there. Now, we've been asked to find out how many photons will have to make that transition to give a total energy pulse of 10 joules. Well, think of the complete energy pulse of light coming out there like that, and it's 10 joules worth, and made up of that 10 joules is all these wee energy level ones here called E. So to find the number of photons, all we have to do is to find the number of photons. Number of photons is take the energy of the pulse, which is 10 joules, and divide it by how much one photon of energy carries, which will be 16.4 times 10 to the minus 19 joules. Once again, we do that in my calculator, we should get an answer of something like 0.61 times 10 to the power 19 photons. You don't need to bother putting in standard form, just leave that as the answer, 0.61 times 10 to the power 19 photons. Now that was a good question, because they've given us a different way. They've given us a electron making a transition. You have to work out the energy, and you have to find out how many of those transitions will make up 10 joules of light. So it's a case of taking 10 joules and dividing it by the energy of one of these photons. Okay, so that's done that energy one. Then let's move on to our next starter question. Remember, you can go back again and you can replay this on the YouTube channel when this little movie is linked up on the YouTube channel. Let's go to the next question then. An electron is accelerated from rest through a potential difference of 2 kilovolts. The kinetic energy gained by the electron, and you have to make your choice. Well, we know that the work done by an electron as it moves through the field, either the work done on the electron or the work done by the electron to get across the field, is equal to W, and that's always equal to QV. It's in the data book. W is the work done. That's the work done, which we're after. And we know Q is the charge of the particle. And V is the potential difference. That's the potential difference, potential difference. You asked to find the kinetic energy gained by the electron. Lots of people will immediately think kinetic energy, half mv squared. No, not the case. That will be the work done. Because remember, in the electric field, if we've got two parallel plates like that, and that's the plus side of the wires, of the sort of plates, that will be the minus side. We know the electric field goes across like that. If you can see the field lines, they go across like that, from the plus side to the minus side. So if you've got a little electron in there, that little electron sits there. Remember, it's negatively charged. If I want to move that electron over to here, it will go itself. It's the field that does the work, because the electron wants to get over there. So the electron will move over there of its own accord. But if I drag that electron, if I drag it over here, so if I drag it to here, sorry, it will want to get back. It will move to there. So the electron's sitting there. I have to do work on that electron to move over here. I've got to pull it away over to the other side. It's a bit like a mother pulling a toddler away from the swing park. The little toddler wants to be at the swing park. The mother comes along and drags the toddler away. The mother has to do work on the toddler to get it back away. It doesn't want to be there. So when I drag something across here, I do work on it. But when the electron moves back the way, the electron then changes its work into kinetic energy. So the kinetic energy gained by the electron is simply the work done, W equals QV. So we'll go ahead and work that out, and quite easy to do. The work done is equal to QV. What's the charge in the electron? Look it up in the data book. It's 1.6 times 10 to the minus 19 coulombs, multiplied by the potential difference, which is 2 kilovolts, which you can write as 2 times 10 to the power 3, and we get an answer there of 3.2 times 10 to the minus 16 joules. And that's our answer. So the kinetic energy gained by the electron is when the work done on the electron is then released by the electron. The electron moves across to the other side. Okay, so that's a very famous one. Just remember the equation, work done equals QV. Remember the charge on the particle. Charge on the electron is 1.6 times 10 to the minus 19 coulombs, the same as the charge on the proton. The proton is the same charge, 1.6 times 10 to the minus 19 coulombs. Okay, let's go to our next starter question. It's a talky one, so let's think about it. The EMF of a battery is the total energy supplied by the battery. Don't know about that. The voltage lost due to internal resistance of the battery. No, definitely not that one. The total charge which passes through the battery. Nope, not that one. The number of coulombs of charge passing through the battery per second. No, it's not that one. The energy supplied to each coulomb of charge passing through the battery. It's that one. The EMF is the amount of energy given to each coulomb of charge as it passes through the battery, and the battery actually gives the coulombs of charge the energy. So that's the one that I want you to remember. It's a definition. What the EMF is, it's the energy supplied to each coulomb of charge as it passes through the battery. And you know that EMFs can be written as the volts. EMF for maybe say a car battery is 12 volts. What does that mean? It means that for each coulomb of charge, 12 joules are given to each coulomb of charge. Each coulomb of charge. And also remember, the potential difference is get the same units, joules per coulomb. But the EMF of the battery from the old words electromotive force, which they thought was given the electrons to push, is actually the energy supplied to each coulomb of charge passing through the battery. So there you go. That's that one done for us. Let's see if there's any more then of this tutorial night then. And this famous one comes up. It shows you a circuit of a diode of some type, and it's asking you which mode is this photodiode working in. Which mode is it working in? Now right away you see the light which is shining into it, and that is the P-type part of it, and that's the N-type part of it. And we can see we've got a battery here, plus side and the minus side, and the plus side is connected to the negative part and the minus side is connected to the plus part. So right away I know that that is working in what we call reverse bias. Now that gives me a clue. Reverse bias. Now, what's happening here? Let's think the way through this one. If we take out this little bit of information here, we can see I'm going to replace the symbol with the actual diagram of the PN junction. I'm just going to have that wee bit of writing so it doesn't confuse us, and bring this over and replace the symbol by the diode itself. Now in the higher, you have to know what a p-type semiconductor means. A p-type semiconductor is a semiconductor which has holes for its majority charge carriers, holes like that. Now the holes are not holes in cheese, the holes are spaces for the electrons to move into. So don't think it's actually physical holes, it's not. The holes, positive holes in higher physics lingo, is spaces for the electrons to move into. The n-type semiconductor, the majority of charge carriers are electrons like that. Now if you look very close at this diagram, you can see that the n-type is connected to the plus part. Therefore, the electrons tend to move that way, and the holes tend to move that way, so you're going to have a depletion layer here. A depletion layer is an area where there are no charge carriers. Now, that particular circuit will not conduct in. Once the electrons have moved out the way, once the holes have moved out the way, there's a kind of standoff, and no electricity will flow because of the depletion layer. Now, if we shine light onto that, what do we create? We create electron-hole pairs. You have to know that. When photons shine on the junction, you're going to create electron-hole pairs. So when light shines on this, you're going to have an electron and a hole, an electron and a hole. And the more light you shine on it, the more electron and holes you create. Now what have I done here? Instead of me having this no man's land here with no charge carriers there, I now have a lot of charge carriers, which means the electricity can flow in the normal way through the circuit, because these charge carriers are here. As long as light shines on it, you will get a current. Take away the light, you take away the electron-hole pairs. They're not made anymore, and therefore you'll not get the current moving through this way because we have the depletion layer. So when we have a diode like this, we say it's working in photoconductive mode. Photoconductive mode. And that's the little detectors you have on your light gates and on the scanners in the supermarket, because when light shines on it, you will get a current. And that current can be detected by the ammeter and can be sent elsewhere into maybe say some circuit to count things or to measure things. So that is, just keep that question back for a minute, that is the description of what that photodiode is working in. It's working in photoconductive mode. What were the clues? The clues were the n-type was connected to the plus. It's reverse biased. When things are reverse biased, when semiconductors are reverse biased, no current will flow. In this case, you do get a slight thing called the leakage current, which is not much, nothing in fact, microamps. But when you shine light on that junction, you're going to create, wait for it, electron-hole pairs. And when you create electron-hole pairs, you're going to create more charges in that junction, which will enable the current to flow across them like that, therefore registering a current. So as long as light shines on this junction, you will register a current. So that's why we call it photoconductive mode. Now, the hidden question for us for this evening, and it's this one here, it's this one. And it says, when light is shone onto the junction at a distance of 40 millimeters, the ammeter reads 16 microamps. Find the ammeter reading when light is shown at a distance of 80 millimeters from the junction. Now, this would throw a lot of people, and that's why I'm giving you this question, because people automatically think of a radiance. They know that the radiance formula I1 d1 squared is equal to I2 d2 squared. What does that mean, all these numbers to you? It means the radiance, the amount of light, the amount of energy power per unit area shown onto something, times the distances away squared, will be exactly the same as the new radiance times the second distance squared. But I haven't got a radiance on that. But that doesn't matter, because I can use the currents for the radiance. And I want to find the reading ammeter, that will be the second radiance. So that's like a kind of inverse square law kind of problem. So the first current will be 16 microamps multiplied by the first distance, 40 squared. And that should equal to the second current reading, which we don't know, but we do know the distance is now changed to 80 meters times 80 squared. So therefore, according to this formula, then the new current should be equal to 16 times 40 squared divided by 80 squared. And that will be, if you work this out in your calculator, I can just make sure you get the answer this one rather than give the wrong answer. 60 times 40 squared divided by 80 squared, and the answer is 4. I should have known that right away. Well, that's a wee bit late in the evening. E2 equals 4. So you'll get 4 microamps for that radiance. And you could have worked out yourself from your knowledge of the inverse square law. If you double the distance, you quarter the radiance, or you'll quarter the current flowing the circuit. If you double the distance, you're going to quarter it. If you triple the distance, you will make it 1/9 of the radiance. So that's a good question to go back and study, because it doesn't mention a radiance, it mentions current, and it's usually linked with the photodiode working in photoconductive mode. When light shining on a junction will increase the charge carriers in here, which means you'll increase the current flowing. Now that's our question for tonight. I don't think there's any other ones on it. Oh, there is. Sorry, there's one last question on it, and I know I have to go over this one with you because the exam's on Thursday. It's the last question, and it's to do with radiation weighting factor. So after this question, we have finished the tutorial. You can go and have a break, and then you can go and replay the tutorial again on YouTube channel once it's launched. Now, I'll send a link to you through Edmodo. Okay, last question for tonight then. The table shows the radiation weighting factor, WR, for a number of different radiations. So for alpha, we have 20, we have beta, which is 1, neutrons 3, gamma rays 1, and X-rays 0.1. Now remember, we have, it says that here, which of the following gives the greatest equivalent dose? We know the equivalent dose H is going to be equal to the absorbed dose multiplied by the radiation weighting factor. Why do we have to have an equivalent, a dose equivalent? Well, because the dose equivalent balances out all the different types of radiation to give us the same effect. What would the same effect be on our bodies? Now, in this particular case, alpha particles have got a radiation weighting factor of 20. So why? When they don't pass through skin and don't go more than a centimetre in the air. But the fact is that an alpha particle has got a massive charge of 2+, which means it's desperate for 2 electrons. And if you ingest an alpha particle, that will try and snatch 2 electrons from your nearby cells, which can cause problems. So that's why we give it quite a big radiation weighting factor, because it is quite dangerous then. Now in this particular case, we've got to go through each one in turn. 8 micrograys, so the dose equivalent for that alpha particle will be 8 multiplied by 20, and that's going to give us 160. Remember, the units change to 160 sieverts, so it'll be 160 microsieverts. What about the beta particles? For beta, it's going to be 170 multiplied by beta. It's 1. That's going to give you 170. It's like the Eurovision Song Contest. That's out in the lead so far. What about the 56 micrograys of neutrons? Well, the radiation weighting factor for that is going to be 56 multiplied by neutrons, 3. So we'll have 3 56s for that one to give us our answer, and we get an answer of 168. So still not out in front, we've still got a leader. What about 160 microdegrees of gamma rays? Well, it looks like a big number to start off with. 160 multiplied by gamma rays, radiation factor is 1. It's going to give us 160. And our last one then, 1,500 microgreys of X-rays. We should see what's happening now. 150, 1,500 times X-rays, 0.1. And that's going to give us 150 microsieverts. So the one which has got the greatest equivalent dose will be this one in here, which will be in fact 56 microgreys of neutrons to give us 160 microsieverts. Remember, the dose equivalent doesn't tell you anything. You have to work out the dose equivalent rate to get a better picture of things. And that was in a previous video, which you can go and study. Well, that's me finished the questions for tonight. Then I can now go back, hopefully, to the screenshot. I'll now go back onto it now, if I can find it. That is, go back to our screen. I can see we've got 3 viewers, which is very good. So that's little tutorial finished for this evening. Now go back and play it on your laptop, your computer, your tablet. I'll put the link on to Edmodo, and you can look back at the questions and answers, how they were done in your own time. I hope you've enjoyed this hangout, and all it remains for me to say is, well, best of luck for your exam on Thursday. You can come in on Thursday morning, and you can study all afternoon, all morning until the exam comes. And remember, from Mr. Mallon, best of luck.